All right, so we're going to continue on solving equations in the context of using exponential equations and logarithmic equations, and today we're going to focus on solving logarithmic. All right, so again, I'm going to go ahead and just walk you through some examples. So first we have log base 5 of 2x squared minus log base 5 of 7 equals log base 5 of 56. And one thing you can do, for some students, solving these equations just feels pretty straightforward. It feels natural to you. For other students, it can be really hard once we start to mix up all these different types of equations. So you have this kind of flow chart that I made. Now that we're going to have kind of a mixture of everything, this can kind of help lead you through the problem. So are there logs or natural logs in the problem? In this case, the answer is yes. It's a logarithmic equation. Are the logs on one side or both sides is the next question. So if it's on one side, you're going to do this. If it's on both sides, you're going to do this. Before we determine what to do next, we do have to use our property of logarithms to condense the problem down. So at the very most, you can only have one log on each side. You can't have more than one. So if I look at this problem, I can see that on the right side I only have one, but on the left side I have two log base 5s, so I do need to condense that down. This is a subtraction problem, so that means I've got division. So I have log base 5 of 2x squared over 7 equals log base 5 of 56. All right. Now, since I have logs on both sides, I can ditch the logs and solve the resulting equation. So both of these have a log base 5. That means that these two things should equal as well. So it's kind of like when we were solving exponential equations. Once we got it to where the base was the same, then we were good and we could finish the problem from there. Same sort of idea. So now I have 2x squared over 7 equals 56. And I'm going to go ahead and multiply the 7 over to the other side. And I get 392. I did not do it that fast. I had it on a separate sheet of paper. And then I go ahead and divide by 2, and I get x squared is 196. And then I can go ahead and square root to get my x alone. And I want to make sure that anytime I square root something, I always put the plus minus there for my answers. And 196 is a perfect square, and so x equals positive and negative 14. So now before we conclude, okay, my answers are positive 14 and negative 14, we have to go back and remember something special about logarithms, and that was that you can't plug just any number into a log. You have to plug in positive numbers. You can't plug in 0, you can't plug in negatives. So we don't necessarily have to check our answer, although we certainly could. What we do want to do, however, is we want to make sure that when I plug in my x values of positive 14 and negative 14, that does not mean I'm trying to take the log of like negative 7 or something. That would not work. So if I plug in positive 14, I have 2 times positive 14 squared. That's certainly going to be a positive number. If I plug in negative 14, I have 2 times negative 14 squared. Again, that's going to be positive. So that means that both of these are good answers. All right, let's do another example. Log base 6 of x plus 5 plus log base 6 of x plus 4 equals 1. All right, so again, we start off using our property of logs so that we can have only one log per side. So I know that I'm going to write log base 6 once, and I know that the plus means that these two things are multiplied together. So I have x plus 5 and x plus 4. I know that when I multiply these, I do have to FOIL them out because I have two parentheses next to each other. You can FOIL them out and then get rid of the log, or you can get rid of the log and then FOIL them out. It doesn't matter as long as you actually do it. So what I'm going to go ahead and do is just wait for a second if I look at my flow chart, it says if I have the log on one side, I need to turn this into an exponential equation. So you can Tootsie Roll. So basically what you're thinking about is I need to undo the log. The opposite operation of logging something is called exponentiating. It's where you make something like a base and you turn this into the exponent basically. So what that process is doing is it's taking the problem from a log and turning it into an exponential function. So if you like the Tootsie Roll idea, you can say the base of my new problem is 6. 6 to the first power equals this stuff. Exponentiating would mean I'm going to put a base of 6 on the left side of the problem and a base of 6 on the right side of the problem. So 6 to the log base 6, those are inverse operations, so they cancel. And that gives me x plus 5 times x plus 4 equals 6 to the first power. 6 to the first power is 6. Okay, so on your flow chart, you can say Tootsie Roll, turn it into an exponential equation, or you can think of this as exponentiate both sides. Okay. So either one of those ways of thinking about it is totally fine. You do the way that you feel most comfortable with. Okay, so I'm going to go ahead and FOIL these out. I can't say x equals -5 and x equals -4 because this does not equal 0. So I've got x times x is x squared plus 4x plus 5x, and then 5 times 4 is 20. Now I'll go ahead and subtract the 6 over and make it equal 0. So I'm trying to think now of two things that multiply to 14 but add to 9, and that would be 7 and 2. And so I have two solutions, x equals -7, x equals -2. And so now I have to think about if I were to plug these into the log, if I was to use -7, -7 plus 5, that's -2. Log base 6 of -2 is not possible. I can't take the log of a negative number. So -7, although a nice number, is not a solution to this problem. And again, you can see it over here, -7 plus 4 would also be a problem. -2, however, is totally fine. -2 plus 5 is 3. I can log 3. -2 plus 4 is 2, and I can take the log of 2. And so x equals -2 is a good answer. All right. Let's say we have log base 7 of x minus 1 minus log base 7 of x equals 2. So this is a logarithmic equation. I have two logs on the left side. I know that I need to condense those down into one log. So this is log base 7. It's a minus problem, so that's division. And so again, I'm looking at my flow chart. I have log only on one side, so I can think of Tootsie Roll turning it into exponential form. Or if I want to think of this as an inverse operation, I want to exponentiate each side to get rid of that log. So I'm going to have 7 to the log base 7, 7 to the second power. These are inverse operations, so they cancel. And that gives me x minus 1 over x equals 7 squared is 49. And then I'll go ahead and I don't want this to be a fraction anymore, so I'm just going to multiply that x to the other side. 49x. I'll subtract this x over, so -1 equals 48x. And then I'll go ahead and divide the 48, and I get -1 48th equals x. And if I look over here, -1 48th minus 1 is a negative, so I'm taking the log of a negative, which I can't have. And the same thing would have happened over here. You would be taking the log of -1 48th, and that can't happen either. So we only had one possible solution, and we just found out it doesn't work. And so that means for this equation, you're going to say there's no possible solution at all. There's no number you could plug in for x that would ever make that equation equal 2. So no solution on these is possible. Let's try another. I want to show you guys one that has an ln in it, just so we can make sure we're comfortable with that. All right, so even though it says ln, this is really a log problem. We do have a log only on one side, but there are logs. And so I need to start off using my properties to condense it down into one log on the left side. So this is an addition problem that means that I need to multiply these together. So 8 times 2x squared is 16x squared. And then from here, I need to go ahead and switch this into exponential form, or I need to undo that log. So I've seen students kind of do this both ways, where I've seen students just kind of memorize that the opposite of ln is e. That's one way to do it. The other way is if you want to write this as log base e of 16x squared equals 4 so that you can see the base, that's fine as well. I have a tendency to think this way. It just works better for my brain, but memorizing that e is the opposite of ln is not necessarily difficult either. So I'm going to go ahead and exponentiate each side. So e and ln cancel because they are opposite operations, or they are inverse operations. E and log base e would cancel out for the same reason. So regardless of how you chose to write that, you would get 16x squared equals e to the 4th. All right. From there, I'll go ahead and divide by 16. So I get x squared equals e to the 4th over 16. And then I'll go ahead and square root each side, so I get x equals plus or minus, since I square rooted. And it will be square root of e to the 4th over 16. So I know from this that the square root of 16 is 4. So plus or minus, I know the bottom of my fraction is going to be a 4. The e to the 4th, you can think about square rooting it, or you could think about what would happen if you had e to the 4th raised to the 1/2 power. So e to the 4th raised to the 1/2 power is the same thing as square rooting. 4 times 1/2 is 2. So that's e squared over 4. All right, so before I conclude that I have two answers here, I do have to check and make sure that when I plug it in, I'm not getting a negative inside of the log. I don't plug it in here because there's no x there, so I just think about plugging it in here. If I have positive e squared over 4, and I do 2 multiplied by that squared, that's definitely going to be positive. If I think about negative e squared over 4, when I square it, it's going to become positive, and it multiplies by 2. So I do have two answers here, and both of them work if you plug them back in. Okay, one last example. We have log base 3 of x minus log base 3 of x minus 1 equals log base 3 of 43. So we've got logs on both sides this time. We do need to condense the problem down so we only have one log on each side. So this is a subtraction problem. That means I'm going to use division. So I have x over x minus 1. And then if I look here, whenever I have logs on both sides, that means I can ditch the logs. So I have x over x minus 1 equals 43. If I don't want this to be a fraction anymore, the easiest thing to do is to just take this and multiply it to the other side. So I have x equals 43 times x minus 1. So x equals 43x minus 43. And then I will go ahead and subtract the 43x over to the left side. So 1x minus 43x gives me negative 42x. And then I can go ahead and divide the negative 42 back over. And so since I have a negative divided by a negative, they'll cancel, and I get a positive 43 over 42. Seems like a funky number, but if you look at it, it's going to work out just fine. So log of 43 over 42 is good. 43 over 42 minus 1. This fraction is a little bit more than 1, so when you subtract 1 from it, it's still positive. And so that means that this really is a valid answer. And of course, anytime you feel like your answer might not make sense, or you're feeling uncomfortable because it seems like a funky answer to have, you can always go ahead and just type it in your calculator. I just didn't do, let me get into a different mode. There we go. I'm going to go ahead and store this as x. So you can always type your answer in and just make sure that it works out. So log base 3 of x minus log base 3 of x minus 1, and that should be the same as log base 3 of 43. And you can see those decimals are the same, and so that means we really did get the right answer. So I don't expect you to check every single final answer if you don't want to. I know these are kind of a pain to plug in. However, checking to see if you can log your answer or not, checking to see if it's an extraneous solution is required every single time. I expect you to check that.